It's my great pleasure to invite and introduce Pranay Sharma from IIT Bombay. So Pranay joined, I think, last year, and I tried to get him to come here or engage in research, and he was very busy. So the only way for him to come here actually was to organize this workshop and invite him for the talk. So that's why to travel 25 kilometers, he really took an year. And his work is actually on federated and collaborative learning. So before he joined IIT Bombay, he did his PhD from Syracuse and also did a postdoc at CMU. So all yours.
Hello. So can you hear me? Is it on? Can you hear me? Okay, nice. Thank you so much for the invitation. Yeah, that's true. So I came to Marine Drive and NCP a bunch of times, but I was not able to converge to TIFR. So today I finally did. So I'll be talking about reinforcement learning in non-stationary environments. So a couple of disclaimers. I'm severely jet lagged. So have you seen a movie called I Am Legend? So there are a bunch of zombies in that movie and they cannot be exposed to sunlight. So that is me right now. And second, so I'm not an expert in reinforcement learning. There are others who are sitting here. So we'll figure all of this together. Okay. Okay. So this work is based on, I can never figure. Okay. Yeah. So this paper, which we put out a few months back. So this is a work with Niharika, who is a PhD student in CMU, Ishika, who was a master's student. I think currently she is a PhD student at UIUC. Gwanan and Gauri, both of them are faculty members at CMU in the EC department. Gauri was my postdoc supervisor. Okay, so we don't need an introduction to reinforcement learning in this workshop, but I'll do that anyways. So we want to do sequential decision making under uncertainty, and it is relevant in a bunch of domains like games or robotics or self-driving cars. I was in Palo Alto till a few days, like till 2 days back, and you see a bunch of Waymo cars driving around there. Like, it's a creepy feeling with no driver in a car, but they are there. But there are also a bunch of applications where there is a non-stationarity in the environment, that the world you are living in is changing continuously. So for example, data centers or financial trading. So financial trading, you can easily imagine that the kind of data you are getting is changing very quickly, and like there might not be any predictability or regularity to this data. Similarly, recommendation systems. So these systems are supposed to evolve with user preferences, which are quite unpredictable, might change over time, and so on. So the problem we want to solve is we want to do well in a time varying environment in the long run. Okay. So there are several things which need to be concretized here. What do I mean by doing well? What is a time varying environment? And what do I mean by in the long run? Okay. So we'll do that in the next few minutes. So this is the overview of the talk. I'll begin with some background in RL and MDPs. Then I'll talk about policy gradient methods in general, very briefly, and specifically something called the Natural Actor-Critic method. And then, because we have to work in non-stationary environments, I'll be talking about an algorithm we proposed called non-stationary natural actor-critic, not a very creative name. And then I'll talk about regret bounds. So regret is essentially what do we mean by doing well, and I'll conclude. So Markov decision processes are the theoretical framework we use to study reinforcement learning. So here we have M is an MDP and consists of several components. S and A are the state and action sets. We'll work with finite sets for both states and actions. P is the probability transition. R is the set of rewards. So at any given time, you might be in certain state S, and you take an action. The environment looks at this action, gives you some reward, and then also gives you the next step you will move to. Okay, so your trajectory consists of such tuples. So you have a state, you take an action, you receive some reward, and transition to the next state. Actions come from some distribution. Given any state, you might pick from an action from a bunch of actions using some distribution, which is in RL called a policy, and R is the reward. And next state again comes from a probability distribution, which depends on your current state and the action. So P is a probability transition matrix, R is a reward vector, and in stationary environments, both this P and R are going to be time invariant, but we'll work with non-stationarity, so these will be time varying. The transition matrices will change with time, the reward vectors will change with time. So how do we measure how well we are doing? There are mostly people study discounted setting. Discounted setting essentially means we care about the reward today more than we care about the reward in the future. So we want to maximize the cumulative discounted reward, which is this infinite summation. So the reward at any time step t is weighted by this discount factor, which is less than 1 raised to the raised to the power t. And the initial state S0 comes from some initial state distribution eta, and at each time instant, the actions are taken based on our policy. Yes. 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 That's what learning is about. Yeah. Yeah. So in this case, assume the policy is fixed. We will get to that. So this is the simplest setting. Yes. The rewards, like, so here I'm assuming that given a state action pair, your reward is fixed. There's no distribution, but those rewards are changing with time. The function that generates your reward is changing with time. So in this talk, we'll work with average reward. Okay, so what that means is that we look at this summation of rewards over a time horizon t. We normalize it by the time horizon and then take the time horizon to infinity. Okay, so there is no discounting happening here. And under ergodicity assumption, so I'll describe what this means later. But under some good assumptions on our Markov chains, you can give a much simpler expression of this average reward. So you look at your reward for any state action pair. The state comes from some stationary distribution and the action comes from a policy. Okay, so that gives your average reward. So this stationary distribution is the distribution induced on your states when you use your policy pi and you have these transition matrix P. Okay. So why do we care about average reward when most people care about discounted rewards? Because discounting essentially introduces a time preference that you care about the reward now more than the reward that is coming in the future. So this is a cartoon which was published in New Yorker a few years ago. And this is basically what companies in the US try to optimize. So average reward emphasizes steady state behavior. So on average, in the long term, we want to do well. Okay, so this is the right notion when the system runs forever, when you want the world to survive in the long run. So for example, in queuing systems, we want to maximize throughput or minimize average latency over an indefinite period. Okay, and other applications are power grids, communication networks, etc. So when we are working with average rewards, we need to talk about relative value functions. Some of you might be familiar with value functions from the discounted setting, but here, because it's an infinite summation, there is no discounting, so there is no guarantee of finiteness. So we need to work with relative value functions. Essentially, what we are saying is that this infinite summation, which appears in average reward, we are looking at how much it deviates from the average reward at each time instant and sum that over time. Okay. And just like we have state value functions and state action value functions, similarly, we have relative state value functions and relative state action value functions. Okay. So state value function is you start from this state and then let the MDP unfold. So what is your relative value for that state? And for state action pair, you start with this state action pair and then let your MDP unfold. So what is the relative gain or loss of your value function for this state action pair? And we have Bellman equations for relative value functions as well. So this is essentially saying that if you want to figure out what is your relative state value function, you take a step, you pick an action using your policy, and what is the state action value function for that state action pair, and you average it over all possible actions. Okay, so far everything is very similar to what we have in the discounted setting as well. So let's very quickly go over and get an overview of what are the different kind of methods, and then we will converge to some class of methods which make sense in our setting. Okay, so the goal is essentially that suppose we run a policy, we get some value function. We want to find such a policy which gives us the maximum value function or which maximizes our reward. Okay, so arguably the simplest methods to do that are value-based methods, which iteratively update the value function and then use those updated values to come up with the new policies. Okay, so they have some problems, like they can diverge with function approximations, etc. Also, you are looking for a policy, but you are going in a roundabout fashion, first computing a value function and then the policy. So how about we work directly with policies? So this gives us policy-based methods where we directly try to learn a policy. Okay, and an example of that is policy gradient methods, where we essentially do gradient ascent in the policy space because we are trying to maximize the reward. So suppose we parameterize our policy with some parameter theta. Okay, this can be the entire policy, this can be some parameter, and we define some performance measure j of theta, which quantifies how well this specific policy depending on this parameter will do, and then we can do gradient ascent. So here, this is an estimate of the gradient for this performance measure. The advantages are that, so this is might not be obvious here, but policy-based methods can help us learn arbitrary policies, arbitrary stochastic policies. Like you want to assign 0.58 probability to some action, 0.15 to something else, and the remaining to something else. You can do that with policy-based methods. It's not that easy with value-based methods. Also, often policies are easier to approximate, although that can be argued for value function methods as well. But sometimes it's easier to inject some prior information about the policy rather than having some prior information about the value function. So there are cases where, yes. Yes. Yeah, but there might be like.
So your non-stationary environment, is it stationary or is it stochastic?
Yeah, also like if you have function approximation, if you have limited information, then you might not have like a deterministic policy as an optimal always. Right.
Function approximation.
But you might have limited information, and in that case, so like I think Tetris is one example where you need a stochastic policy, which you can't get with a value function based method. Sorry.
Is it a partially observed?
Yeah. Okay. So we are inclined towards towards policy based methods. So again, with policy based methods, you can have actor only methods where you have an actor which is trying to learn the policy, and these can be applied to continuous settings, but sometimes they suffer from the gradient that you have to use for the policy gradient that can have a high variance, which can hurt your convergence. By the way, anyone recognizes who that is? Okay. Am I the only one who watches movies? So this is Robert De Niro. Yeah. Okay. I was hoping you would get the next picture, but I doubt it now. Okay. So actor-only methods suffer from high variance. So people came up with actor-critic methods. Who recognizes these two? Roger Ebert is the right guy. Who is left? Huh? Okay, so this is Gene Siskel. These guys, Siskel and Ebert, they had a very famous show called At the Movies. They were movie critics. Okay, you're supposed to know this. Okay, so then you have an actor and a critic. The critic tries to estimate how good a specific policy is, and then based on the estimate of the policy of the critic, the actor can then update its policy. Okay, so you have a critic telling you how well you are doing. So a summary of how we get to the function we are working with. We want to find a policy which maximizes the average reward. Critic only or value function based methods might diverge in a few settings. So we work with actor. So actor only methods might be a choice, but these have high variance. So actor-critic methods combine the best of both worlds. And then there is something called natural actor-critic methods, which enjoy some better convergence guarantees because they utilize second order information. So everyone heard of Newton's method? So just like Newton's method gives you a little more information and hence better convergence compared to gradient descent, the same idea is utilized, a similar idea is utilized in natural actor-critic. And it gives you global optimality under certain conditions.
But you start close.
Sorry?
For Newton, you have to start close.
Yeah, so quasi-Newton method. Okay. So the problem statement is we are working with it in infinite horizon average reward setting, and we have non-stationary environments, and the approach we decide to work with is natural actor-critic kind of method. Okay. Yes.
For example, for activity or those are not exactly for this particular setting, but for the next setting.
Say that again. The drawbacks are not exactly for
setting. Those are general drawbacks
for stationary setting. Yeah. So we are working for a harder problem, so we are hoping that, yeah. Okay, so next let's, so we are done with the background. Let's go to natural actor-critic. So as I mentioned, Newton's method or quasi-Newton methods. So this is how we are going to update our policy parameter. We have the gradient. So more importantly, first thing, the performance measure that we are working with is going to be the average reward. Okay, so given your current policy pi, which is parameterized by theta, our performance measure is going to be j of pi theta, the average reward for this specific policy. And now the actor tries to update the policy to get to a better average reward. So it uses the gradient for this average reward, and it also uses another matrix because you need a matrix for a second order method. So first, the gradient is given by policy gradient theorem. So this looks complicated, but it's relatively simple. So you are trying to update the policy. So you should have gradient of the policy in some way. That comes here. So you have gradient of log of the policy. Okay. And then you want to find out how good a specific policy is. That is quantified by your value function. And this is an expected value where the state is coming from the stationary distribution and the action is coming from the policy. Okay. So gradient for the policy, how good the policy is, and expectation. And this matrix is the Fisher information matrix. So this is simple enough. The expectation is over the same distributions again, and it's just an outer product of this vector. So grad log pi, gradient of the log of the policy, and then transpose the same vector. So this gives you a matrix. Okay. And then because this is a random rank 1 matrix, you are taking expectation over some state and action pairs. Yes.
The Hessian.
This is not the Hessian.
Is that why it's quasi?
Sorry?
Is that why it's a quasi?
Yeah, so that's why I said it's not Newton. It's a second order method only. Okay. So that was.
Second order.
Sorry?
Still a first order.
Approximately. A lot of caveats, yes. I said Newton's method because everyone has heard of Newton's method.
Also the expected second derivative.
Oh, right. This is the expected Hessian of the, yeah. So you can replace this with minus Hessian of this thing. Yeah. Yes, thanks.
It is one component of Hessian or is it like the entire?
It's the entire Hessian. Yeah. Thanks. Okay, so with this complicated looking update, let's see if we can simplify this somehow. So if we have softmax parameterization, what that means is that we are essentially doing softmax over our policy parameter. So suppose theta is our policy parameter. Given each state, we can compute the policy with this expression. So here S, the state remains fixed. You compute the softmax function of this component of the vector which has state as S. Okay, so all the components are non-negative, they all sum to 1 for each state. So you get a softmax parameterization. And with this parameterization, it turns out that this natural gradient based update simplifies to something which is nice. So given your current policy, you can update it using your state action value functions. Okay. So in the denominator is just normalization where you are summing this over all the actions. So does this update remind you of something?
Please.
Sorry?
Please.
Yeah, it should remind us of a number of things. This is also exponential weight update, right? So multiplicative weight updates, hedge algorithm, it should remind us of a number of things. Okay, so this is simple enough, but the problem is we don't have this q pi theta. Okay, so that's where we need the critic. So the critic estimates these q value functions using TD learning. So this is a simple enough update. Given your current value for each state action pair, you just update it using one step transition. Okay. So if we were in state S, took action A and transitioned to the next state S prime, and then took action A prime in that next state, then these are the Q function values. Eta is an estimate of the average reward. Why do we need eta here? Because we are working with relative value functions. We were not working with exact value functions. So this gives us the critic estimate for the value function. And that gives us the natural actor-critic algorithm. Okay. So you start with some initialization. Let's assume uniform policy. And initial value functions are all 0. Initial reward estimate is 0. And then we unroll our trajectory. At time t, we took some action and observe a reward. Get to the next state using this probability transition and take another action. So we have ST AT, ST plus 1, AT plus 1. Because we have observed this reward, we can update our average reward. So this is just a convex combination of what we observed and our existing estimate. Okay. So eta t times 1 minus gamma plus gamma times r, the current reward we observed. This is an estimate of the average reward. Critic we have already seen, actor we have already seen. So this gives us the basic natural actor-critic algorithm. Yes.
What is pi r?
This is a projection.
What is r?
So R is some bound on. Okay, I was going to talk about it tomorrow.
Radius r set.
Yes,
You are not using
not today. Not today. That will hopefully come tomorrow. Yeah.
Why?
Say that again. Yes. Oh, so here you want qt plus 1. You can do that. Slightly more complicated analysis, but you can do that. Okay. So in our eventual algorithm, it leads to slightly more complicated analysis, but you can do that. Okay. So far the rewards were fine, the transition probability was fine, it was a simple stationary environment. But what if both of these are changing over time? What if our environment is non-stationary? So that brings us to the algorithm, but not immediately. Let's see. So when we run natural actor-critic under stationary environments, then so the critic estimates the value function for the current policy. So critic tells the actor how good your current policy is, and then the actor uses that to update its policy. Okay. And if I go back a few steps, so here alpha and beta are the step sizes for the critic and the actor. So if alpha is much bigger than beta, then the critic is changing much more rapidly compared to the actor, right? Maybe a more intuitive thing to do would have been that you keep the policy fixed and then change the critic multiple times so that the critic converges to the value function for the current policy and then update the policy. A similar effect can be achieved if you choose alpha much larger than beta. So the critic is taking much larger steps compared to the actor. So the actor is much more conservative, while the critic is within a single step, it is able to estimate the value function. Yes.
The main critic should be able to provide us with some correction. Is that the right way to think about it?
It is telling you how good you are.
Which by telling you that you're making a mistake.
So it is giving in the policy gradient, you have that Q value, right? So it is sort of, also in policy gradient, you can replace that Q with the advantage. So the relative function, how good your action is for each state. So it is also giving you the signal if you are good, like, so it is giving you more information. Yeah.
The actor decides what the next policy should be. The thinking tells you whether you have made the movement in the right direction by telling how good that. Did it improve the value function? Can it be so? Did it improve the value function? Because sometimes these policies themselves, the actor updates are depending on the critic updates themselves. So the critic tells how good the policy is, and the actor could use the value estimates to update. So in that sense, the correction. Probably critics actually evaluate to the report and that is fed back to that. Thank you.
Okay, thanks. Yeah, so in the stationary setting, if your critic step size is much larger than the actor critic step size, then the critic would achieve good enough estimates of the current for the current policy. Now, when we have non-stationary setting, yes. What is
Known. Yeah. What is known in the station?
the environment is not known. It's just not changing with time.
The results.
Yes. So in the stationary setting, for Natural Actor-Critic, there was a paper in ICML last year which showed, I think, epsilon to the -3 kind of guarantees. So translating to the regret, eventually when we look at the regret guarantees, you get T to the 2/3 regret. We'll have much worse regret, but still sublinear. Sorry? Yes. With linear function approximations, which I'll hopefully talk about tomorrow. Yeah. Okay, so under non-stationarity, we assume we have a sequence of MDPs. So the state action pair remains same, but the transition probabilities and the reward functions are changing over time. So now the actor is chasing a moving target. It is no longer looking for the best policy. It is trying to find the best policy at each time instant. And the best policy is evolving over time, right? So earlier, the stationary distribution was fixed. Now the stationary distribution will change over time. And earlier the reward function was fixed. Now the reward function changes over time. Okay. So the actor is chasing a moving target now. So the challenges are that we need to explore more aggressively because whatever we knew so far might no longer be valid. Also, we need to balance forgetting old environments with learning new ones. Okay. So, which brings us to the non-stationary variant of Natural Actor-Critic. So, essentially, we will run the same algorithm, but in multiple segments. So, we divide the entire time horizon into n segments, each of equal length. And at the beginning of each segment, we will restart. So, we will forget whatever we did so far. So, this looks suboptimal, and most likely it is, but so far this is the best known. So, we restart at the beginning of each segment, and within each segment, it's essentially the same algorithm. We start with uniform policies and initialize the value function estimates to 0, the average reward estimates to 0, and then we unroll the trajectory. So note that now the reward functions have a time subscript, the transition probabilities have a time subscript, and the updates look exactly the same as before. The difference is only in the reward and transition probabilities. Yes?
Is that how the pizza happens?
No.
Why would you tell us?
So they might change arbitrarily. We only assume that the cumulative variation is going to be sublinear. So I'll define the cumulative variation in a second. Okay, so this is essentially Natural Actor-Critic, but it is happening in segments. The entire horizon is divided into segments, and within each segment, we are running Natural Actor-Critic. Yes.
T is index of two things. It seems like I'm estimating pi star T, but pi T plus 1 is some sort of iteration. That's still the same here.
Right. So at time T, pi T star was the optimal policy based on the average reward of the environment at that time instant. That's a mouthful. So at each time instant, the environment is changing. If I'm at the current time instant T, given my current reward functions and the current environment, if I could somehow find out what the actual stationary distribution is and find the average reward, that would correspond to my pi T star.
This I agree, but the actor itself, like,
Yeah.
even in the stationary case, you're updating the policy over time.
Yes.
You're updating the policy as you gather samples.
Yes.
I thought that's what the actual mirror descent step is doing. Pi T plus 1
Yes.
here is actually updating over time.
Right.
Updating over iterations as opposed to updating across time.
So the time index and the iterations are the same thing here.
Okay, they are the same.
Yeah. So it's not a double loop algorithm. You cannot run a double loop algorithm here because the environment changes continuously.
I see. So I am updating for the next time.
Yes.
Based on the previous.
So like actually your pi T plus 1 would want to track pi T star. So yeah, so like there is this one step lag because at this time instant, you only have knowledge of what you have observed till time step t. Okay, maybe we'll clarify this in a few slides. Okay, so let's look at how this performs, this algorithm. So our initial goal was we want to maximize the time averaged reward in over a long enough time horizon. But with non-stationary environments, we slightly modify our performance metric and we say that we are interested in something called a dynamic regret. And what that means is, so at each time instant, this is sort of the best you can do. So pi t star is the optimal policy at time instant t, and jt pi t star is the average reward for that policy. Okay. So this is the maximum average reward at time instant t. This is the actual reward which we get with our algorithm. And we want this quantity, we want this difference to be sublinear. Yes.
Without any conditions of seems to be too high.
Yeah. So I'll come to the conditions in hopefully in the next slide. Yeah. Yeah, you are right. I agree with you. Yeah. So given the environment or MDP at time t, and pi t star is the optimal policy at time t in this environment, this is the average reward for that optimal policy, and we are comparing against this optimal average reward at each time instant. Okay.
Is it also meaningful to look at the static regret?
Yeah, I mean, if you're
Fair, offline do everything, but still have to feel the signal.
it's like the OCO setting as well. Like if you don't expect the environment to change by a lot, then static regret makes sense. But if
Suppose I post that,
Hmm.
don't think more about it.
in the static regret setting, I am not sure. Yeah, I think we went to dynamic regret in the very beginning itself. Yeah, but the papers I have seen like don't really talk about static regret in the non-stationary setting. Yeah. Okay, so this is our performance metric, and you can look at static regret. Oh, right. Sorry. Yeah, these papers, like the classical papers, do look at static regret. But the more recent ones, for example, like David Simchi-Levy and his group has a bunch of very well-cited papers on non-stationary RL. Like all of them. I think this paper was a precursor to this paper, and this was the one that introduced this dynamic regret metric. Yeah. So static regret not been considered in the recent papers. I should rush a bit.
Always have to score people.
Okay.
Just stop wherever.
Yeah. So the variation budget. So what are we imposing? The question which was asked earlier. So we are assuming that the cumulative variation in the reward function and the transition probabilities is bounded. Okay. So this difference, how much your reward function is changing from one time instant to the next, added over time, and how much are the probability distributions changing from one time instant to the next, added over time. These things we assume to be sublinear. Okay.
Instead, what you have to think they start with.
Right. I think that turned out to be more difficult when like this was easier to work with. Because this was easier to work with because these quantities appear quite naturally in the analysis. But yeah, that's a good question. And we impose a uniform ergodicity assumption at all time instant. So what that means is that given any environment and any policy, this kind of a condition has to hold. So you start from any state and you let the Markov chain run, and you compare the distribution at any time instant tau to the stationary distribution, and you get the distances in terms of TV distance become exponentially close as you proceed with the Markov chain. And we assume this condition holds for all potential policies and for all environments. Okay. So we have ergodicity uniformly at all time instants for all policies and for all environments. Sorry?
Is it across different T's or is it?
It is, yeah. Yeah. For all PTs, this has to hold. Yeah. In that case, yeah, so I think I'll let this be the last slide. So in that case, if we choose our step sizes for the average reward, for critic, for actor in this way, and this is the number of times we restart. So this is the number of segments we divide our horizon into. Under that condition, this is the dynamic regret we get. So we have t to the 5/6 and this delta t, which is summation of the cumulative variations of reward functions and the probability distributions. We have 1/6 in the variation. Okay, I'll skip this. I'll discuss this tomorrow. I just want to point out the existing lower bound from this paper, which is t to the 2/3. Okay, so we are quite a way far from the existing lower bound. Yeah, I'll talk about these things tomorrow. But just to conclude, so we were interested in coming up in studying model-free setting of RL, and we wanted a policy-based algorithm for the infinite horizon average reward setting. We settled on natural actor-critic method, and for non-stationarity, we had to do some restarts. And we gave what, to the best of our knowledge, is the first dynamic regret bound in this setting. Tomorrow, I'll finish up what I left. I'll also try to give a proof sketch, some intuition for why this gap exists between our bound and the existing lower bound. Also, in the step size choices, I said that like they depended on the variation budget. What if you don't know the variation budget? What if you want some function approximation? You don't want the tabular setting. So all of this, hopefully, I'll cover tomorrow. Yes. Yes. Yeah. So again, that is something we are thinking about. What if we can like actively decide how long the next segment will be? But so far we don't have anything on that. Yes.
Inside one block,
yeah. Because at the beginning of each segment, you initialize the policy to be uniform, right? So suppose you ran the algorithm in a single segment, your policies have gone to some place. Now, suppose the environment has changed a lot, right? So like suppose something had a very high probability, but now the environment has changed so much that a completely different thing needs to have a high probability. So it's easier to get a fresh restart with uniform probabilities rather than forcing our like already skewed probabilities in that direction. Yes. Yes. Thanks for the compliment.
All right, no more questions. Let's thank Pranay. Hello, can you hear me?
All right. So it's a great pleasure to introduce Gugan Tope. And I'm told now, not by Gugan, but somebody else, that it's supposed to be pronounced as Guhan and not. So people in TI4 only knew him Gugan, but the corrected sound should be Guhan. So I think Gugan is the only person who was here before I joined. So he joined just before I did as a faculty member. He was a student here. He graduated from TIFR in 2015, worked with Borkar, and his work is primarily in reinforcement learning, but in the past he has also done geometry, not only just dynamic programming. I've also played cricket with him, so I'm pretty sure he continues to do so now. And as he says, what he does these days with his students and collaborators, he builds reinforcement learning algorithms that behave even when the world doesn't. And the world definitely is not behaving these days. You saw what happened 2 days ago. So, and they chase guarantees, which are monotonicity, sample complexity, and the occasional speed up, and apply them to problems that didn't ask for RL but needed it, such as histopathology and blockchains.
Yeah.
So let's welcome. And I should definitely say something. So even when he was a student, many of us thought that he would make a good teacher because his way of thinking or explaining things were very pedagogical. And I think he's not mentioned this, but he's already got some teaching about from IISc, if I'm not wrong. So
Work. I'll try to make sense of all of that. And in my tomorrow's talk, I'll come up or discuss some ideas of how we are going about fixing it. Okay, so this is joint work with my colleague Aditya Gopalan, who is also from IISc. Right, so if you try to do deep reinforcement learning and you get frustrated and you search for blogs, you will come across some comments like this. The unspoken truth about deep reinforcement learning is that it holds significant potential. It remains fundamentally disappointing. So significant potential is elaborated over here. Here are a bunch of applications. I've tried taking pictures of faculty members in IISc who are working on these topics. So here we have some robot which uses reinforcement learning to figure out how to walk. This is the histopathology project that I was involved in. Here is something on LLMs. Here is something on games. Here is something on stock market prediction. So all of this at some level, reinforcement learning has made its mark. Nevertheless, it has been fundamentally disappointing. So again, I searched for some blog which mentioned this, and I sort of created a word cloud based on the number of times different issues pop up. And if you have constructed such a word cloud, you must be aware that the size of the word corresponds to the frequency it appears with. Okay, so for example, sample efficiency appears multiple times, training instability appears multiple times. Okay, and you can see that there is one small thing over here, lack of theory. Okay, and I believe that some of these issues can be fixed if we fix the theory or get the theory right. Okay, so I'll go over some preliminaries of reinforcement learning. I'll touch upon some of the things that Pranay spoke about, but I will go into it in certain depth. Okay, so a high level summary of reinforcement learning can be put in this way. At its core, reinforcement learning involves an agent that is interacting with the environment. The agent must sense the environment state, take an action to affect the state and get some reward, and the agent's goal is to maximize, in some sense, either a discounted sum of rewards or some suitable sum of rewards, which I will refer to as value function, and I'll formally define it later. And the key challenges in reinforcement learning is that these transitions and rewards are often uncertain, and more importantly, the states and actions are often very large in number. Okay, so the environment that I spoke about, we typically model it as a Markov decision process. So unlike Pranay's talk, I will presume that this MDP is stationary. I will tell you that here itself there are a lot of challenges and we will try to focus on them. So whenever I say something is an MDP, I will characterize it by 5 things. One is the state space, and in this talk I will presume that it is finite. Then we will have an action space. I will presume that the same action space is available at each of these states. Then we have what is called as the transition probability kernel, which basically says what's the probability that the environment moves from state S to state S prime under action A, and on this transition you get some reward which is a function of the current state and action. It can also be a function of current state, action, next state. It can be a distribution based on these things, but we will presume that it's a deterministic function. And then we have some discount factor. The discount factor, as Pranay highlighted, in some sense characterizes how much do you value a unit of reward that you get today compared to that you will obtain at the next time instance. Okay, and this is typically a number that is less than 1. So we have an agent. The agent has to interact with the environment, and the way it interacts with the environment is formally defined via what is called as a policy. And to keep things simple, we will presume that the policy is actually stationary, which means that it's a function from the state space to a set of distributions on the action space. I think there is a typo. This should be calligraphic S and calligraphic A, and delta of A means the set of distributions on the action space, right? And when the agent uses some policy like mu to interact with the environment, which is an MDP, this results in an experience trajectory, which basically means you will get a sequence of state, action, reward, next state, next action, reward, and so on and so forth. And in this talk, I will presume that you start with some arbitrary state and action. The reward then is a function of this state and action. This state is sampled from this transition matrix P. The next action is sampled from your policy mu. The reward again is a function of S1, A1, and so on and so forth. Now, once you have a policy, you want to know how good that policy is, and a formal way to quantify how good a policy is via what is called as a Q value function. This is actually a vector. You can also view it as a function. This vector is denoted by Q mu. It's a vector whose size equals the product of the state and action spaces. So if your state and action spaces are very large, this vector sits in a very high dimensional space, and the SAth coordinate of this vector is the expected discounted sum of the rewards that you would get when you interact with the environment with your policy mu. That is, these actions AT are chosen according to this policy mu, right? So with this vector description of Q value functions, one can now define what an optimal policy means. So policy mu star is optimal if its Q value function is bigger than that of any other policy for every S and A. So Q mu star SA, right, should be bigger than Q mu SA for all mu and all SA. One can show existence of such Q value functions, right, and one can show that such Q stars are unique, but there can be multiple policies whose Q values are these Q stars. And at a very high level, or I should say slightly lower level, the reinforcement learning goal is to find an optimal policy using the experience trajectory. Okay, that's the goal of reinforcement learning. All right. So now the question is, how do we get hold of this optimal policy? So towards that, we appeal to a framework called as dynamic programming, and we will define certain operators. These are popularly known as the Bellman operator. So there are two kinds of Bellman operators. One is corresponding to a fixed policy, and the other is what is called as the Bellman optimality operator. Each of these operators takes a vector whose size equals the state action product. It takes an input which lives in a space whose dimension is the product of the state and action spaces, and spits out output again which lives in such a big dimensional space, and T mu of x. So if x is living in this space, T mu of x is a capital S times capital A dimensional vector, and the SAth coordinate of this is given in the following way. The way to interpret this is, suppose you have a one stage problem, okay, where the terminal reward is x, right? And in this one stage problem, if you interact or take the only action using your rule mu, what is the expected returns that you would get, right? So this can be viewed as a one stage problem where the terminal reward is x. This is the immediate reward plus the terminal reward that you get, and you take the expectation of this quantity over S prime and A prime, where S prime comes from your transition matrix and A prime comes according to your rule mu. Okay, and this SNA determine this SNA. And then there is something called as the Bellman optimality operator. The difference between this and this is that here this A prime is chosen according to mu, whereas here this A prime is the one that maximizes this quantity over here. Okay, and that's why it is called as in some sense the Bellman optimality operator. And the nice things about these operators are that they are gamma contractions in the L infinity norm, which means that if you take T mu x minus T mu y, and if you take the L infinity distance between them, then it will be less than gamma times x minus y. Similarly, T satisfies some condition like this. And the importance of these operators lie in the fact that the Q value function of a policy mu is a fixed point of this operator T mu, and the Q value function of the optimal policy is actually a fixed point of the Bellman optimality operator. Okay, so these two equations in some sense bring to like highlight the importance of these operators. All right, so now the question is, how do we find the optimal policy? So I will go all the way back to 1950s where these ideas were discussed in some sense for the first time. So the natural algorithm that one would consider is what is called as value iteration. So you want to find mu star, and I think I did not mention this, but one can show that the let me just go one more slide back. So one can show that this mu star is actually greedy with respect to q star. Okay, so q star is a vector. When I say mu star is greedy with respect to q star, what do I mean is you look at the q star values for a fixed s, for a fixed state s and different actions a. You take mu star to be that action which at state s to be that action which maximizes over q star sa, and that is what is called as a greedy policy, and one can show that a policy that is greedy with respect to q star is actually the optimal policy. Okay, all right. So one can see that to find optimal policies, it suffices at some level to find q star, and because q star is a fixed point of t and t is a contraction, this is one of the simplest algorithms that one can cook up. You start with some arbitrary, sorry, I think there is a typo, there should be some value estimate q0. So you start with some arbitrary value estimate q0, you apply t on that, get q1, apply t again, you get q2, and you keep doing that, and perhaps at some point you get bored and you say that okay, the values are not changing by much, so you stop at that point, and then you define or declare the policy that is greedy with respect to your terminal qt as an estimate of your optimal policy, and one can quantify how good this policy is and so on and so forth. So in contrast to value iteration, there is another algorithm which is called as policy iteration. Okay, here the distinction between value iteration, the difference from value iteration is that we actually try to find intermediate policies as well. There notice that there were no intermediate policies, but we are directly trying to find q star. Here in contrast, we also try to keep track of some policy, and the way we do it is you start with some arbitrary policy mu0 and you repeat these two steps iteratively. Okay, so the first step is what is called as policy evaluation, which means that whatever is your current policy, you try to find out how good it is, and to find out how good it is, technically you have to find q mu k, which again recall is a fixed point of this t mu k operator, and one can show that that fixed point is actually a linear system of equations for a fixed mu. T mu q mu equals q mu, that fixed point equation is actually a linear equation. So this is like solving a SA dimensional linear equation. So you solve that, get hold of your q value function for your current policy, and then you define your new policy to be the one that is greedy with respect to your current q value function. Okay, so you start with mu0, get q mu0, define mu1 to be the one that is greedy with respect to q mu0. Now you have a new policy, and now you calculate q mu1 and repeat the story, right? And in this case, one can show that the algorithm will terminate in finitely many iterations, and whenever you don't see any difference between mu k plus 1 and mu k, you terminate, and whatever is the output policy, you declare that to be the optimal policy, and one can show that it will indeed be the optimal policy, right? And recently, by recent I mean like roughly 25 years back, okay, Sham, Kakade and Langford, they actually proposed a variant of policy iteration which they refer to as conservative policy iteration. Here again you have these two steps as in your policy iteration, that is you have a policy evaluation step and a policy update step. The policy evaluation step remains unchanged. Whatever is your current policy, you try to find its q value function. The difference is in the policy update. If you go back to policy iteration,
the policy update was whatever is your Q value function, you define the new policy to be the one that is greedy with respect to Q mu K, right? So you go full greedy, whereas here you try to pick a convex combination between your current policy and the full greedy policy. So you define the new policy to be some convex combination where alpha is your convex combination coefficient plus 1 minus alpha times mu K, and the way you pick alpha is you pick alpha to be the one that in some sense maximizes the performance difference, okay, and in particular you try to maximize a suitable lower bound on this performance difference, okay. So let's go over this carefully. Q mu K is a vector, nu prime is in some sense a distribution on the state action space. It could be some initial distribution or it could be something that changes, right, and this then becomes a scalar, okay. So this nu transpose Q mu K, the prime over here is like the transpose, so this becomes a scalar. So this is like the average Q value function where the average is over some state action distribution, and this again is some average, and you look at the difference between these two scalars and find an alpha that maximizes this. Ideally we would like to maximize this, but that is hard. So what you do is you look at a quadratic local approximation to this gap and you maximize that quadratic approximation. So that is what I mean by, you pick an alpha that maximizes this, right, and again you break if your Q mu K's are not changing anymore. So at a high level, what do we know about these methods? Okay, so yes.
For this conservative EI output, so about spreading the benefits across the state actions rather than.
So to be honest, okay, I actually don't know what is the advantage of conservative policy iteration. Many people have written lots of stories about why it may be beneficial. At this point, there is no theory that I can strongly correlate it with those, but let me wager a guess. So I'm wagering a guess, right? So at a high level, so there is something called as tabular setting and function approximation setting. Tabular setting means, we work with the value of your, how good your policy is. We work with vectors that sit in a essay dimensional space and we hope that somehow we can get as good a approximation of that Q mu K itself. That's what roughly tabular means, right? And in tabular settings, I'm not really sure if conservative ideas really help. Okay, I feel the benefit of conservative ideas come with function approximation. In particular, I feel that when you are using these conservative updates, you may be able to escape some local attractors. Okay, so that's the guess. Okay, so just to summarize again, my guess is that in tabular settings, I'm not really sure if conservative ideas necessarily help. But in function approximation settings, these conservative ideas could help escape some local attractors. I will show some pictures in my talk tomorrow to illustrate on that aspect. Is that okay? Yeah. So those are a vector that at a high level, this is a vector whose dimension equals the product of the state action. It could be some distribution that you care about. For example, certain state actions may be more important to you. It's at this point, it's a fixed distribution. Is this okay? But it could also be changing. So, they sort of obtain an upper bound, which is in some sense agnostic, or I know they get an upper bound which depends on nu. So whatever be your nu, you could come up with a, sorry, I shouldn't say upper bound, a lower bound on this gap. Okay.
Yeah, I was going to ask if it is how is the prior affecting, but is there some sort of a gradient at some of?
See, in tabular settings at a high level, the prior will not affect because the optimal policy is unique. I shouldn't say optimal policy, the Q star is unique, right? So this, I mean, in tabular settings, the limit will be the same, but how fast you go there will be affected by, this choice of nu prime. In particular, you may care about going close to Q star in certain state actions and ignoring others. In those cases, these things will definitely help. Okay. All right. So what do we know about these methods? Okay. So for value iteration, one can show that because we are working with fixed point iterations, one can show that there is exponential convergence. on top of that, we can also guarantee monotonicity. By monotonicity, I mean that the vectors actually monotonically improve. Notice that these are vectors and not scalars, and these inequalities over here are coordinate wise inequalities. Okay, so if you impose some condition like this on the initial estimate, then one can show that your Q0, Q1, Q2, they will actually satisfy some monotonicity like this. For policy iteration, we have some monotonicity guarantee, but in some sense it is better explainable. By that I mean that here the Q values of your policy themselves monotonically improve. That is, Q mu 0 is less than Q mu 1. So if you obtain mu 1 via policy iteration, it is guaranteed to have a Q value function that is better than Q mu 0 on every state action. That is, on every coordinate it is guaranteed to be better, right? And one can also show that this policy iteration is actually a Newton step to find the 0 of this function. So as Rahul pointed out, when you are very close to Q star, one can actually show that it has quadratic convergence rate. So of course that is local convergence guarantees. And for policy iteration, one can show that the algorithm will terminate in finitely many steps, but those number of steps could be very large depending on the state and actions, right? And as far as I know, I don't think there are any uniform per step improvement bound. That is, how much does Q mu k plus 1 differ from Q mu k? Can we provide some guarantees like that? As far as I know, I don't think there are. For conservative policy iteration, one can show that there is some notion of monotonicity, but the monotonicity is in the expected sense. By that I mean, here nu prime Q mu 0 is a scalar, and these scalars actually monotonically improve, right? And in this case, at least if you go and read this conservative policy iteration paper, they say that their main goal is to provide some per step improvement bound, and they actually provide a per step improvement bound, and using those bounds one can show that this gap actually converges at the rate of O of 1 over k. Yes. So you can fix a nu. For example, if certain state actions are more important, you give more weight, otherwise you can choose it to be uniform. Okay, and these constants over here will depend on the choice of mu and so on. Okay, all right. So the summary is that, okay, life is good when you are having the ability to work with Q mu k's and so on and so forth. Okay, so I have roughly 15 minutes, right? 20. Okay, so life is good if we are somehow able to estimate these Q mu k's and come up with a policy update that depends on these Q mu k's. So far so good. Now the question is, what happens when you take these dynamic programming inspired ideas to reinforcement learning? Okay, what happens? So first let's go back and recall the challenge. Okay, so in real world problems, one of the main challenge is that the state and action spaces are very, very large. Is this okay? For example, if you go to control settings or robotics, your state and action spaces could be infinite, right? Or if you go to some games or LLMs, here while the state and action spaces could be finite, they could still be combinatorially very, very large, right? So the challenge here is that whether you work with value iteration or policy iteration, conservative policy iteration, you cannot find the quantities of interest exactly even if you give infinitely many samples. Okay. So in particular for policy iteration and conservative policy iteration, to do the policy update, you need knowledge of Q mu k. So you won't be able to get it exactly whatever you do. And in value iteration, there is this TQK that you use to get QK plus 1. And this quantity again sits in a SA dimensional space. And that SA dimension we are presuming is very, very large, right? So hoping to get exact estimates of TQK or Q mu k is very, very challenging. And on top of that, there is uncertainty, right? Recall that these T operators and these T mu operators involve an expectation, and that expectation is defined with respect to some transition probabilities. And in reinforcement learning, we don't even presume that we have access to these transition probabilities. They have to be implicitly learned by interacting with the environment, collecting samples and so on. So to summarize, in reinforcement learning, there are two key challenges. One is this huge state and action spaces. The other is the sampling issue. Is this okay? So we have to deal with both of them. I will focus on this issue of huge state and action spaces, how people currently do. I will tell you what are the issues with the way people currently handle this huge state action space idea. And in my next talk, that is tomorrow, we will come up with a different way of handling these large state action spaces. Okay. So as Pranay also hinted, we make use of what is called as function approximation. In particular, I will focus on the case of value function approximation. Okay. So as I said, in large state action settings, Q mu or TQ, which is the quantity that is used in your value iteration and policy iteration updates, they sit in very high dimensional spaces. So what you do is, instead of trying to compute these Q mu or TQ vectors exactly, you try to come up with a function class and you say, okay, what's the best proxy for, Q mu and TQ, and you say, okay, let's just, do whatever happens with this, right? So the idea is you try to approximate Q mu and TQ with some f which comes from some nice class of functions. For example, you could work with linear function approximation, in which case you fix some matrix phi, right, and you ask what is the best theta that you can get so that phi theta is approximately Q mu. This should not be equal to, this should be an approximate sign. Alternatively, you want to know, can I find a theta such that Q mu SA equals theta transpose phi SA for all SA approximately, right? So that's the idea of linear function approximation. And you could also use neural networks, which are more popular, and the idea here is that you sort of presume that there is a vector that captures all the weights and biases of your neural network, and once you have a neural network architecture, that somehow determines a function class, and the goal is, can you somehow adjust these weights and biases so that the f theta that you eventually get mirrors Q mu as closely as possible. Okay, so either you could work with a linear function class or neural networks and somehow try to get a good proxy for Q mu or TQ depending on what you are trying to do, right? And here are some of the popular ways of finding such an f. Okay, so I'll just go over them carefully. So the first is the natural idea of projection. Okay, so you want to approximate Q mu, okay, and you have some function class calligraphic f. You try to find an f which is closest to Q mu, right? So this is one of the objective functions you could consider in setting your theta values in linear function or nonlinear setting. But the challenge here is, to do this projection, you need the knowledge of Q mu, right? So how can we know the knowledge of Q mu? Because recall that Q mu is a fixed point of T mu, and T mu is involving some expectation which we don't know. So we will have to estimate Q mu using these samples, right, and also do projection. So that's the reason people came up with an alternative to this. Instead of trying to find the projection, you try to find a fixed point of the projected Bellman operator. Okay, so T mu is your Bellman operator, and pi f T mu is the projected Bellman operator, and you try to find the fixed point of this, and one can show that the fixed point of this under some conditions is reasonably close to the projection. And the idea here is that you don't need the knowledge of Q mu. So in some sense you can simultaneously do Q mu, estimation of Q mu and the projection. Okay, so this at a high level tries to do this, but the challenge over here is that the fixed point of this projected Bellman operator, or the update rule to find this, cannot be viewed as a SGD, right? So what they do is, okay, instead of working with this, let me work with some other objective and try to is this my issue or okay? So here they say, okay, let me try to come up with some TD error and I'll try to write an SGD for this, and then they realize that, okay, there are f's at two places, my gradient calculations become very difficult, so I'll replace one of the f's with my current estimate and only work with other f, and they have a bunch of these ideas, right? And even if you, in similar approach, right, if you want to approximate TQ, you could do something like this. Okay, so I want to say how pervasive these ideas are. You can see some of the biggest algorithms in reinforcement learning that are around. Okay, this is LSPI, this is fitted Q iteration, then you have double Q learning, DQN, DDPG, TD3, TRPO, PPO, safe policy iteration. So almost all algorithms at the policy evaluation level use some ideas like this or some variants of this to address the specific issue that they are dealing with. Okay, however, Burtsekas, okay, in his 1996 textbook, okay, so if you actually look at neurodynamic programming, which is a textbook that appeared in 1996, and if you look at his discussion on approximate policy iteration, which basically means you do policy iteration where the Q value functions are approximated either using linear function or neural networks, right? And his recent survey from 2011, which is titled Approximate Policy Iteration, a survey and some new methods. So if you look at the textbook and these new methods in this survey, he actually repeats what he spoke about in the textbook in some more detail. What he says is, at a very high level, approximate policy iteration methods are based on the idea of approximation in the value space and on the hypothesis that a more accurate approximation will yield a better policy through policy improvement equation. Okay, so let me elaborate. If you recall the policy iteration algorithm, it said that if you have mu k, find q mu k, find a policy that is greedy with respect to q mu k, then you are guaranteed that q mu k plus 1 will be better than q mu k. Okay, that is what is called as a policy improvement lemma, and one can guarantee that the next policy is better than the previous policy. Here, unfortunately, we don't have access to q mu k, right? So what you do is you come up with a proxy for q mu k and you try to take a greedy policy with respect to the proxy for q mu k. And the hope is that if your f is very close to q mu, if you be greedy with respect to f, okay, the next policy is guaranteed to be better than q mu, mu itself. That's the hope, right? However, Butsekas has identified several issues with this hypothesis, and he has pointed out that while this is a natural hypothesis, it may not even be true in some problems. And he has given a lot of examples of how the convergence behavior then becomes very complex and involves potentially damaging oscillations, which describe their initial description long ago, are still not well understood. Okay, so I would like to highlight a bunch of such issues, right? So here is the DQN algorithm from 2015. This is a paper that in some sense made a big splash. Okay, it appeared in Nature paper, and here is the pseudocode for this algorithm. And at this place, you can see that you are trying to minimize estimate of TQ minus Q. So this is your current, this is your variable Q, and Yj here is like estimate of TQ hat. Okay, so if you remember, I said you do this TFK minus 1 minus FK, right? So here this is like an estimate of TFK, right? And you think of theta as the only variable and you try to find a theta that minimizes this quantity. So at a high level, this quantity this step over here is trying to minimize TFK minus F, and F is the only thing that they are viewing as a variable, right? Now what we did was, this is from our recent paper, this is going to appear in Transactions of Automatic Control. What we did was we took the DQN algorithm from that paper, cooked up 100 random MDPs, right, fixed some hyperparameters, allowed this algorithm to run, right, and we compared how does the initial quality of the policy compare with the final quality of the policy. Okay, so we would like that the algorithm should learn, which means that the final value should be better than the initial value, right? And since we are working with negative, if I am not wrong, if you are, points over here learn and points over here do not learn. Is this okay? By do not learn, I mean that the new policy should get better than the previous policy, right? And you can see that roughly half of them are below the diagonal, roughly half of them are above the diagonal, right? And it sort of puzzled us. Ideally, we would expect that maybe a concentration of the points is below the diagonal and only a small fraction is above, which perhaps appears due to some stochastic sampling noise and things like that. But we noticed that at least we couldn't see any pattern. And then we said, okay, can we try to understand what exactly is this DQN algorithm trying to do? So what we did was, we took DQN, replaced the neural network with a linear function approximation and kept everything as before. So it has a bunch of steps. Whatever that original algorithm was, we retain everything except that we replace the non-linear function approximation, that is a neural network, with a linear function approximation. Okay, so in particular, we took a two-state, two-action setting, which is like S times A is 4, right? So the Q mu's, Q star all live in a 4-dimensional space. And what we do is we work with linear function approximation that projects them on a 2-dimensional space. So the theta 1, theta 2 or phi times theta 1, theta 2, that will give you a proxy for your Q mu and Q stars. And what we did was, to keep it at least meaningful, or at least for us to analyze it carefully, one of the columns of your phi matrix was chosen to be Q star. Is this okay? So in particular, this star over here, which corresponds to 1, 0, that is the, if you multiply 1, 0 with phi, you will get the first column, and this is the value function corresponding to your optimal policy. And what we did was, we started estimate which is very close to this optimal policy, right? And then we ran your linear DQN algorithm. Okay, linear DQN meaning you take DQN, replace the neural network with linear function approximation, and you run it. And on different runs, we saw that it was somehow going and settling at different places. On few of the runs, it indeed went to star, which is the value function corresponding to the optimal policy. But on different runs, it actually went and settled somewhere else as well, right? And we looked at the greedy policy with respect to these value estimates, and we saw that along the green trajectory, there was a unique greedy policy. But along the red trajectory, the greedy policy kept jumping between two different policies. Okay. So then we asked, can we provide an explanation for why it is going and settling over here, here, and why is it jumping between these two greedy policies, right? So for that, a quick explanation is here. To come up with this, we had to use some stochastic differential inclusions and so on and so forth. But at the end of the day, the explanation can be compressed to this figure. So you have DQN, and in DQN you have this T operator, and the T operator involves a max. Because of the presence of max, the dynamics is non-linear. However, with linear function approximation, one can show that the dynamics becomes piecewise linear. Okay. In particular, in this setting where we have two states and two actions, one can show that there are 4 deterministic policies. For each of these policies, there is a cone where if you take any theta here and look at phi theta, and you look at the greedy policy with respect to phi theta, then for every theta in this cone, the greedy policy will be the same, right? So similarly, the greedy policy here will be the same, but it will be different from the greedy policy here, and so on and so forth. So every deterministic policy will have its own greedy region, right? And within each greedy region, one can show that the dynamics of linear DQN is some linear dynamics. Okay. So you see that there are some colors and there are some diamonds with certain colors. So this has to be interpreted as the limit or the equilibrium associated with the dynamics in this region. So in certain cases, the limit or the equilibrium associated with the dynamics could be within the cone, and in certain cases it could be away from the cone as well. Is this okay? So now let's keep this figure in mind and try to explain. So you can see that there is some faded parts. So the faded parts are basically the initial jumps. We actually work with decreasing step sizes here, so they jump and eventually settle down. So we have faded those parts so that it doesn't confuse us with the main story that happens at the end, right? So let's try to interpret the blue part. So eventually, since the step sizes become small, you settle and you try to follow this dynamic. So this dynamics pushes you towards this, and this is what we see over here. Now the initial noise could push you, and it could sometimes push you here, and in which case you try to go to this region, and this is what happens. But something interesting happens here. So when you are in the red region or the pink region, you try to move here, and as soon as you cross over to this side, your dynamics changes and you try moving over here. Is this okay? So it's like, you are on this side, you feel the grass is greener on the other side, you go over there and you realize that the grass was better here, you come here and you keep doing that. And since you keep jumping between these two greedy regions, right, you eventually settle on the boundary where, the dynamics will cancel each other, and there is some place where the 0 is in some convex combination. So one can show that. So you settle neither here nor here, but on the boundary, and because you are settling on the boundary, you will sort of keep jumping up and down, and that's why the greedy policy corresponding to the estimates keep jumping between two different policies. Okay, so the high level summary is that you could have such traps, okay, between greedy regions, and you could keep oscillating between them, and even if you put in more data, whatever you do, unless you add enough noise to escape, you will be stuck basically here. Is this okay? And with this understanding in place, we tried to come up with an even more challenging setting. So we came up with another MDP. Again, it has 2 states, 2 actions, and we chose some function approximation phi suitably. and for that the associated piecewise dynamics was the following. So let's understand what happens over here. So wherever you start, like let's say you start over here, you try to move to the red diamond, right? But as soon as you move over here, you will be pushed to this place. Okay, similarly, if you start in the green region, you try to move over here, but as soon as you move here, you will be pushed towards this dynamics and so on. And one can see that in this setting, the blue diamond is actually a globally asymptotically stable equilibrium. And one would expect that if something is globally asymptotically stable, maybe that corresponds to a good place, like going there is perhaps nice. One can actually show that the greedy policy associated with this vector over here is the worst of the 4 policies that is present over here. So you may put in more data, you may put in more training, you will eventually land up in a place and you see that the performance is stable, but the greedy policy at that point will be the worst among all possible. Okay. Now one may say, okay, you have only used linear function approximation, maybe these things don't happen with non-linear function approximation. So here is a paper by Viral Kumar from 2021 ICLR, and he has used non-linear function approximation, he has used DQN, and one can see that here there is average return, and these are some different environments in Atari setup, and one can see that here again you start learning, and then you start collapsing and you don't go back. Okay. So you again go up, go down, go up, go down, go up, go down. Ideally, we would like that this actually goes up and settles somewhere, but here you can see that it goes up and goes down, right? So then one of you may say, okay, maybe DQN has these issues, maybe the other algorithms, in particular the conservative variants, maybe they are good enough. Okay, so here is a paper on PPO which appeared in 2024 NeurIPS, which looks at PPO, which is proximal policy optimization. This idea builds upon the conservative policy iteration idea, right? And here again, you can see a few environments which have been chosen from Mujoko. These are some different hyperparameter choices. In each of these cases, one can see that the performance actually gets better, and then you start falling, right? And this is what is called as performance collapse. And I hope you agree that in reinforcement learning setting, we would like that as you put in more data, you get better policies. But here one can see that as you put in more data, you can actually collapse and you need not be able to recover back. Okay, so on time, let me give the concluding slide. Okay, so what are the takeaways? So at without function approximation, which I'll refer to as the tabular setting, there your value iteration, policy iteration, conservative policy iteration, they have strong guarantees and they will help you find the optimal policy, right? However, when you go to function approximation setting, all these guarantees go for a toss, right? And when you work with these approximations at a high level, I feel people are just hoping and praying that it works. They put in more function approximation, they put in more assumptions and hope and pray that look, if my function approximation, if it is rich enough and if I'm greedy with respect to that good estimate, maybe my new policy improves. But all those guarantees are, all those things at this point I feel are only at a level of hope. At least I have not seen any papers that probably show all those things without imposing very restrictive assumptions like Bellman completeness and so on and so forth. So the goal for tomorrow is to ask, how can we extend some of the properties that we have studied for value iteration, policy iteration, conservative policy iteration to the function approximation setting. Okay, so this is what we will see tomorrow. Thank you.
All right, there are quick questions. You can put them now. You mentioned the class of functions which we try to approximate onto.
Yeah.
Do you know how it depends on like the properties of the class, so like the busy dimension or something like that of the class itself?
What depends on that?
On how like whether the approximation breaks or not, whether it depends on the class.
See, I'm not sure I know what is the connection with VC dimension and things like that. Okay, but what they typically presume is what is called as Bellman completeness. Bellman completeness basically means that if you take any vector f in your class, apply T, that is the Bellman optimality operator on that, so you will get TF, and you hope that TF lies within your class itself. That is what is called as Bellman completeness. And sometimes they work with approximate Bellman completeness where we presume that TF can be approximated within an epsilon neighborhood within your function class. So these are some notions, but the problem with these Bellman completeness is that it is not monotone in nature. By that I mean, if you have a function class, let's say by some hook or crook, it turns out to be Bellman complete, you add more functions to it, it is not guaranteed that the Bellman completeness will continue to hold, which at a very high level seems very strange that more functions in your function class should only help, right? So at some level I feel, at least I feel, okay, that this Bellman completeness is perhaps not the right way to capture some basic notion of learning. It may be useful for getting a very good estimates of policies and so on, but I'm not sure for some basic notion of learning Bellman completeness should be required. Okay.
Yeah, it's also not a catastrophic bucketing.
Yeah, so that is our guess. Okay, so what we believe is that when you work with these projected Bellman fixed points or things like that, the projection operator depends on your current estimate of your optimal policy, right? So my guess is that when you sort of move closer to some estimate of the optimal policy, the projection operator will change because the value estimates have now changed, and now you are sort of moving to some different target. And in my so we have proved this in the linear dequent setting rigorously. That's why I'm saying I'm guessing. But in PPU and all those things where instead of being full greedy, you be incrementally greedy, like you move your current policy estimate incrementally to the greedy policy that is corresponding to your value estimate. But if you recall, it has an advantage function, and you try to push the policy to like the gradient of the policy parameter towards the advantage function. So incrementally or conservatively, you are still moving towards the greedy policy itself. So we feel that whatever we have learnt in linear DQN, while the greedy regions may look very complex and so on and so forth, but still we feel that once you are targeting something, and when you move to this region, your policy changes, your target changes, and you could go over there. And if that target turns out to be some local attractor, then there is no way you can escape unless you add like sufficiently high noise and so on. So my guess is that this is what is happening over there. That could also happen. I mean, these are all things that Bertsekas has shown in the model based setting. By that I mean where you actually work with T operators itself. So there also you could, with function approximation, you could jump between multiple policies, and you could start here, you take some greedy policy, you go here. By go here I mean that you don't know Q mu k, but you only know a good estimate of Q mu k. So you go over there, you take a greedy policy with respect to that, you move here and you come back. Is this okay? This won't happen in tabular settings because of the policy improvement lemma, which says that you will always keep improving. The monotonicity is there. So that will prevent any cycles from forming. But in function approximation setting, these cycles could form, and that is perhaps what is explaining what is happening. Okay.
You mentioned about that two-stage reflection model.
Yeah.
So what is theta 1 and theta 2 there? How is that parameter related?
Yeah, so as I told you, when we work with this linear function approximation, so Q mu in our example is like a 4 cross 1 vector. Okay, you can either view it as a 2 cross 2 or 4 cross 1. So phi here is a 4 cross 2 matrix that we choose, and theta is a 2 cross 1 vector. So phi theta will give you like a 4 cross 1 vector, which will be a proxy for your Q mu or TQ, depending on whether you are in the value iteration side or the policy iteration side. Yeah.
I mean, the moral of the story, as I understood it, was that approximating functions is not necessarily going to give you quantum scheme with respect to policy improvement. But in RL, you're never really applying the Bellman operator itself, right? You're only getting.
I mean, in an average, you are applying. You may not be applying on a per step basis, but if you look at, like, when you do the stochastic approximation analysis or SGD analysis, you sort of don't look at the immediate update, but you look at the expected update, right? So when you sort of take your step sizes to 0 and look at the asymptotic behavior, in the asymptotic setting, you actually are applying, I mean, in some setting, the expected behavior. And that expected behavior could involve a Bellman operator, for example. Like if you look at Q learning in tabular settings, there also you would have similar settings, like you are saying, we actually work with samples and so on. But if you look at the convergence analysis of tabular Q learning, at the end it will look like Qt plus 1 is, it will be like TQ minus Q, right? So there indeed the Bellman operator's contractive nature is helping show that Qt actually goes to Q star. Okay.
Or if there are more questions, take it at the lunch. Thanks.